Hello, and welcome to the Civil Engineering Tech program's pre-recorded prep lectures. This one dealing for the class of structural mechanics with the topic of stress and strain and how it functions. Stress and strain. What is it? Well, we say stress is force over area. So if we take three objects, I'm going to take this object and make it Portland cement concrete, 4-inch diameter. Then I take a piece of steel, same height, 4-inch diameter steel, and I take another piece, 4-inch diameter, and we'll call this styrofoam. So we have styrofoam here, and we apply a 1 pound load to it. 1 pound. Stress, which is symbolized by that Greek character. What is my stress? We can make that a little bit better. What is the stress on each one of these objects? Now, we're assuming, this is a major important factor, that this equation holds true if the object is able to maintain its structural integrity. If it loses its structural integrity, these equations don't count. But what we're doing is we're evaluating the object now based on its external loads, how it reacts to its external loads being applied to it. And so what is the stress on each one of these? We got three totally different types of materials here. We're assuming that they're all homogeneous, isotropic, linear elastic. What is the stress on each one of these materials? Well, we know that area of a circle is pi over 4 times the diameter squared. So, if we have that, we know that the area for a 4-inch diameter is going to be 12.56. So my area for a 4-inch diameter is 12.56 inches squared. So, my force is 1 pound divided by 12.56. So my stress is what? 1 divided by 12.56 gives me 0.08 psi. Over here I have 1 pound divided by 12.56 inches squared of steel, which once again causes me to have a stress of 0.08 psi. And finally I have 1 pound on top of styrofoam, and the styrofoam has an area of 12.56 inches squared, which once again produces a stress of 0.08 psi. What does this show us? This shows us that stress, even though I have three totally different types of materials, is not a function of the material. Stress is not a function of the material. We're assuming that the material is homogeneous, isotropic, linear elastic. But stress is not a function of that material, given that the material is structurally stable. If the material is able to maintain its shape and maintain its structural stability, its elasticity, then it's not a function of the material. It's a function, stress is a function of Stress is a function of the geometrical shape of the object, not of the material of the object, of the geometrical shape of the object. That is what stress is. Stress is a function of the geometrical shape. So wait a minute, that doesn't make sense. We got three different types of materials, but they all have the same stress, but they're not reacting the same. If I look at them, they've deformed differently. I mean, I see that. Now, even though we only have 1 pound on it, it's hard to tell the strain with regards to the concrete and steel, but we definitely see a little bit of pushing action going on in styrofoam. Strain is a function of the material. Strain is a function of material. That tells us how far something's stretched. Strain, which we identify with this symbol, is the change in length over the length. How far did the thing compress versus the original length? As we can see, we're going to get significant strain here, very little strain here, and very small strain, but a little bit more than the steel here. Change in length over length. So we will get some strain, but it'll be minor in the first two, but we're going to see some significant strain in the third, because strain is a function of the material, not of the geometrical shape. Let's talk about stresses. Stresses. There are 4 basic types of stresses that you need to be aware of, 3 of which are vital. First one, axial. This comes in 2 forms. This comes in tension and compression. Meaning that if I have an object right here, I can put axial force on it this way. That being compression. Or if I wanted to, I can put it in tension. But the force is acting along the object. So it's axial along the object's axis. That is axial stress. The stress resulting from loads being applied along the axis. And so you take this cross section, let's say it was a concrete cylinder, and we're going to compress it. So let's take this concrete cylinder, we'll say it's a 6-inch diameter. Say this is a 6-inch diameter concrete cylinder, and we're going to put 80,000 pounds of stress on it, or pounds of force on it. So I put 80,000 pounds in a 6-inch diameter. What's its stress? Well, we know that stress is equal to force over area. My force is 80,000 pounds. My area, pi over 4 times 6 squared. So I get stress acting on this of 2830 pounds per square inch. That's the stress acting across this cross section. Is a stress of 2830 psi. That's an axial stress. The next stress that we're going to talk about is shear. And shear is perpendicular to it's a shearing force. It's how we resist the shearing force. So we have the same cylinder right here, and we put a shearing force across this cross section right here of 80,000 pounds. Across that cross section, we'd have a shearing effect across this cross section. Stress equals force over area. The area is the cross-sectional force to which that shear is acting through. So this would once again be our pi over 4 times 6 inches squared. And our force would be once again 80,000 pounds. And we'd end up with 2830 psi in shear. That'd be our shear stress coming across that section. Let's look at something else a little bit more applicable. So, if we have a plate, here's one plate, and down below it we have a second plate. And we have two bolts. Holding that plate together. And these bolts are, so one bolt, we'll say they're 3/4 inch bolts. I'm going to put an axial force in tension on this. And we'll say this is, say 2,000 pounds. This is a 1/2 inch thick plate. And this is a 1/2 inch thick plate. And we'll say this is 6 inches wide. So we have 6 inch wide, 6 inch wide, and we're pulling on it with two bolts in the middle holding it together. What's the axial stress in the steel? And what's the axial in the plate? And what's the shear stress in the bolt? Because if we look at this bolt right here, we have a bolt. We have one plate. If we turn this plate around, we have one plate right here. And we have a second plate right here. And we have a bolt right here coming down through, two of them actually. And right through here, that's going to be our shear plane. So, on the plate themselves, what do we have? Well, let's take this, that, no. So let's see, on the plate, we have an axial stress that's tensile. And my tensile stress is going to be force over area. And we're going to look right at this point right here first. So the end of the plate. Force over area, we have a force of 2,000 pounds divided by a cross-sectional area of 6 inches by 0.5 inches. So I have a stress of 2,000 divided by 3. Oops, let's change this to a 3/4 inch plate. So, let's say a 1/4 inch plate. Let's go 1/4 inch plate. 1/4 inch plate. So this would be 0.25 inches. So 2,000 divided by 6 divided by 0.25 gives me 1333 psi. So the stress along this zone right here is 1333 psi. Now let's check the shear of the bolt. Once again, we said we have a plate here and we have a second plate here, and we have the bolt, two of them, coming down through here. And we're having that shear stress right through here. The diameter area equals pi over 4 diameter squared, which is pi over 4 times 0.75 inches squared. So my area of one bolt is going to equal 0.442 inches squared. So my shear stress, on my bolt is force over area, which is 2,000 pounds, divided by, I have 2 bolts, times 0.442. Which my shear then on my bolt is going to be 2264 psi. So I have a shear on my bolt right through here of my bolts. The shear force on my bolt is 2264. And then I also need to calculate the shear stress right at this failure plane. And we'll get into that later when we get into bolted connections. But you can see we have an axial stress and a shear stress acting at the same time on 2 different pieces. Axial stress on the plate, shear stress on the bolt. The third type of stress is a bending stress. And we're going to cover this much more in detail later on. But in effect, if we have a beam and we bend it, the way it bends in order to produce an internal moment equal in magnitude opposite in direction of the externally applied moment, so it bends. And if we take a little cross section right here, and we look at it, what's happened is this beam has bent in and stretched out. So the original shape pushed in up top and stretched out at the bottom. So at this neutral axis right here, we have a lot of compression going on here, compression, and we have tension forces, axial tension forces down here in tension. And this produces our internal moment, which is equal in magnitude opposite in direction of our externally applied moment. And if we were to take a look at the magnitude, at the surface, right up here where it's pushed in the most, we're going to have the most stress because we're going to have the most force, C, and then it's going to come down to the neutral axis, and then we're going to get a lot of tension coming up and back, and so down at the base we'll have the most amount of tensile forces because that's where it's stretched the most. So this is a zone of compression increasing as we get to the surface, going to 0 as we get to the neutral axis, and same with the tension. Most when we get down to the bottom, very little when we get towards the neutral axis. Like I said, we're going to cover this much more in detail because this is a really cool and very important concept to understand. This bending stress. is very important to understand. And so we'll cover this much more in detail, but this is the concept. And what's happening is you have stresses at every point along this beam that you need to be able to calculate at any depth. Because what we do, we change the material's function. If you remember, stress is a function of geometry. So stress is a function of geometry. Since we have the most force in this area, up top and the bottom, where do we typically see most of our mass or geometrical shape? It'll be at the top and at the bottom. Where do we have the least amount of load? In the middle. And thus the concept of the I-beam. You have a lot of your area where you have a lot of your stress, a lot of your area where you have a lot of your stress, and teeny tiny amount of area where you don't have a lot of stress. And that's the concept of the I-beam. We're going to be getting into that, like I said, significantly later on. The fourth kind that I'm not going to talk about hardly at all is torsional stress. From torsion, this is a Mecke thing. It deals with the twisting effect. It is important, but as long as you understand the three principles, as long as you get out of this class the axial, the shear, and the bending stress concepts, as long as we focus on these stresses and understand these, we'll be doing very well. And these are the three I want to focus on. So we talked about stresses, and stress, once again, is a function of the shape. Strain is a function of the material. Once again, looking back, the way the concrete's going to react is going to be different than the way the steel's going to react. It's going to be different than how the styrofoam reacts, even though they have the exact same stresses. The material will act differently. The stresses are the same based off of the geometrical shape of the object, but the strain is different. So we need to understand the effect of the shape and the effect of the material. So, if we look at the material, and we have our object, if we have a length, L, and we put a load on it, it's going to compress. It's going to compress. It may not compress much, but it is going to compress some. The amount this drops, under load from here to here is called delta L. Our strain, which is the symbol of that, is equal to delta L over L. So our strain is the effect of how much it goes down divided by how much it originally was in terms of length. As you can see, the strain value of styrofoam is going to be significantly higher than of steel and of concrete. So that's strain. Now, as this stuff comes down, like I said, once again, this is a function of the material. There's also another property that goes on. When we push down, what happens? Looking at this material, and this is a bad example, but it gives you the idea. This is foam. When we go and squeeze down, what else is going to happen? When we squeeze down on this foam, what happens? As I squeeze down, it does what? It also bulges outwards. Not only does it go down, but it's also going to get slightly bigger. So, as you can see, the thing's going to bulge out. Its diameter is going to increase as we compress it. This is called another strain because it's straining outward also as we compress it down. There's a relationship between the two. It's called U, which is called the Poisson's ratio, which relates this effect. U is the strain sideways versus the strain axially. So the strain axially, the amount it compresses, that strain, versus the sideways strain, there's a relationship called the Poisson's ratio. And that's what it relates. It relates how far this thing bulges out to how far it compresses down, the Poisson's ratio. And the E sideways would be change in W over the original W. Just like this was the change in L over the original length of L. So that's what the Poisson's ratio is. Both of these relate the material. Okay, we have the shape, the stress, and we have the material. There should be a way we can relate those, and there is. Hooke's law. Hooke's law says as long as you have an elastic, homogeneous, isotropic, linear elastic material, E is going to be equal to the stress over the strain. Let's take a look at that. What is that trying to tell me? Well, if I take a spring and I put a weight on it, and I measure this is 0, and I start doing a little recording, and I say weight over deflection. How far did this drop? If I put 5 pounds on it and it drops 1 inch, then I put 10 pounds on it and it drops 2 inches. If it was homogeneous, isotropic, linear elastic, and we hadn't reached the elastic limit yet, what would happen if I put 0 pounds? I took all the weight off. Where would we go back to? 0. Let's say I put 2.5 pounds on. How many inches of deflection do you think I'd have? Exactly, 0.5 inches. If I put 20 pounds on, how much do you think I'd have? 4 inches. But let's say this was our elastic limit. Once we loaded it beyond 20, we went beyond elastic. This is our elastic range. And once we go beyond that, we get into plastic. So if we load this up to, say, 30 pounds, how many inches do you think we'll have? No, let's say it was 6 inches. And then when we go back down to 0, what happens? Are we back to 0? The answer is no. We're now at, well, let's not say 6 inches. Let's give it some plastic range. We'll say 7 inches. So we're at 7 inches. If we take the load off, we're back down to 1 inch. This is permanent deformation. So permanent deformation. Let's take a look at it graphically. Stress versus strain. Load versus deflection. We can put any load we want on it. And as long as we're inside the elastic limit, this is my elastic range, then we have a slope. And if you remember, the slope of a line is y over x. That's the slope of a line. E, the elastic modulus, is equal to stress over strain. Same exact thing. We're getting the slope of this line right here. Once we hit this, so I can put a load onto it, I can put a load on and get this amount of deflection. Then I can take that load off and put this load on and get that amount of deflection, put this load, get that amount of deflection. On down the line, as long as I stay inside my elastic limit, but what happens once I go beyond that? I go into the plastic range. I get some wayward stress right here. I go into the plastic range. I start getting more load because I'm putting more load on it, more stress, but now I'm deforming, and when I take that load off, I still come back on that same slope, but now I have no load, but I have deformation. This is permanent deformation right here. Because I loaded it into the plastic range, I've achieved permanent deformation. When I took the load off, it went back through the elastic zone, slope, and that's my permanent deformation. And so I could fail the structure. In terms of what we're going to be doing, we're going to operate inside the elastic range in this class. There is some very good designs done in the plastic range, but for structural mechanics, in terms of introduction, we're going to operate inside this elastic range, talking about the elastic modulus. So in summary, we're talking stress, which we had axial of both tension and compression, shear, bending, and torsion, which is weak. We had strain. We had the Poisson's ratio. And we had the elastic modulus. Once again, very major concept, this is a function of the geometrical shape, the geometry. This is a function if you put an external load on. Stress is a function how the shape handles that. The shape provides resistance to that external load. How? By stress, and it's a function of the shape and geometry of the object. Strain and Poisson's ratio, the deformation that results is a function of the material. And they're related through the elastic modulus, which relates, is the function that relates stress over strain. Stress, strain, elastic modulus. These are the major components on how a material handles an externally applied load. What are the mechanisms internally of the material handling an externally applied load? These are the mechanisms through which that material will handle it. It'll handle it through its geometrical shape by inducing stress. the material will react by straining through the elastic modulus, as long as we're still inside the elastic zone. The bigger the shape, the smaller the stress, the smaller the stress, the smaller the strain because of the material. These are the components of how these interact and how material, an object, is able to resist an externally applied load, assuming, once again, that it's homogeneous, isotropic, linear, elastic, and assuming that the structure has maintained structural integrity, meaning it hasn't gone beyond its elastic limit. Once you go beyond the elastic limit, these equations change. Assuming we're inside that zone of elasticity, we're homogeneous, isotropic, linear, elastic, and we've maintained structural stability, this is how a material, an object, will withstand an externally applied load. And this is a summary of, once again, stress and strain introduction with regards to structural mechanics. Thank you.